So we're going to work with the matrix equation AX equals to B and work on doing a vector product and some other components here. So, whoops, get that off. Okay, so the main part here is going to be working with those linear combinations we talked about before and working with AX equals to B, basically. So we'll pull that up here. Get a little Word doc going. So wrong one. There we go. So what we're talking about, AX equals to B, that's where all three of these are basically vectors. And A actually is more of a set of column vectors or a matrix. So basically we have A is that matrix. It looks like this. We have X over here itself is a column vector, and B in this case is also a column vector. So when we do that, we actually get something that looks like A will have components, maybe A11, A12, A11, A12, A21, A22. X will be a column vector. Say maybe X has X1 and X2 as representatives, and B is that column vector, so it'll be B1, B2, just to make sure we understand what's going on here. So in the way we were talking about linear combinations before, when we look at this component, we're going to be able to express that as linear combinations as well. So if we look at that, what we really mean to say is we're going to break this up into a linear combination. So we're going to get something that looks like this: A11, A21 times X1 plus A12, A22 times X2. That kind of linear combination. Which is very similar to the example they gave you here, where they have AX is equal to 147,258,369, and they're multiplying it by minus 1, 2, minus 3. So when they do that, they're taking the minus 1 out and multiplying it by the matrix here. Notice, because this is a scalar, it doesn't really matter whether it's to the right or to the left. And because this is a scalar, it doesn't matter whether it's to right or left. They're doing theirs 3 by 3. I just wrote ours 2 by 2. So that allows them to do this combination. And you can see the minus 1 times that. And then eventually they add up those linear combinations to get minus 14, minus 16, minus 18. So the result of this multiplication is going to be B1, B2 as vectors. So that's a really important kind of way of doing it. It allows us, actually, it gives us a way of multiplying this out. So we can see in that example that we've actually got a way here to multiply out a set of matrices. So we've got some examples here. For example, here we have 1, 2, minus 1, 0, minus 5, 3. So that's one matrix multiplied by a column vector. And we can see that when we multiply that out, that's 4 times the 1, 0, 3 times the 2 minus 5, and 7 times the minus 1, 3, and allows us to work that out to 3, 6. I might make a note of that when you look at that particular example. This is an important feature of it, is this matrix is 2 rows and 3 columns, and it's being multiplied by 3 rows times 1 column, that tall bit. And you notice when you multiply it like that, that the inner parts match here. That when you're multiplying two vectors or matrices, that you actually have those inner parts match. And the result is what's left over, which is the 2 by 1. On the top, we had the same thing going on. If you notice here, we had a 2 by 2 here. This is a 2 rows times 1 column, so the result is going to be 2 rows times 1 column. The inner parts match, the outer parts define the result of our multiplication. This is extremely important. If we were to try to do something in reverse, for example, if we tried 4, 3, 7 times, in this case, 1, 0, 2 minus 5, minus 1, 3, in this case, which one comes first really does matter. If we try that, this is a 3 by 1, and this is a 2 by 3. Notice the inner parts don't match. So if I tried to do that, it would be impossible for me to do, and we have to be careful about that. We are not going to take the 4 and multiply by the first part and the 3 and the second part and the 7 by the third part. So right, left, left, right is not always going to be the same. So we have to be careful about that part. That time sometimes is confusing. So another way of thinking about this, and I'll show you a new example here, is just plain multiplying matrices, which we'll do later on, but it's an important feature that we could talk about now a little bit, and that is the fact that if we do multiplication by matrices, we exactly will do that. That multiplying matrices is really multiplying the row by the column, each individually. So we take this row and multiply it through this column and this row, and we multiply it through this column. Okay, just kind of what you're seeing here with the linear combinations. So that does allow us to make that calculation and to get in the end a vector b. What's also important is if we actually compare this to the augmentation, the vector in vector b that's augmented, that actually brings us back to what we had originally, which was perhaps a system of equations. I'll write that as ax1 plus bx. Let's do that differently. Let's do a1 x1 plus a2 x2 equals b1, and then a2 x2 plus, let's do a3 and a4 x2, and that's b2. So this is 1, 2, 3, 4, and notice this is 2 equations, 2 unknowns. If now I augment the system, but I do it slightly differently, I could augment it completely, and I would get, representing the x1, the x2, and the b, would be a1, a2, b1, a3, a4, b2. But another way to represent the same system, if you look at it, would be for me to write this as an ax equals to b, and that would be the a1, a2, a3, a4. And notice now what I would do is I'd put the x1 and x2 in a column to the right of the matrix, and over here would be b1, b2. In other words, the augmented system that we solved before now can be represented by the system ax equals to b. And we have a vectored representation of the system. So that's why that ax equals to b is really important, because ultimately we're going back to representing a system of equations this way, where a1, a2, a3, a4 are merely the coefficients, a1, x1, x2 are the variables, and b1, b2 are the constants or coefficients on the other side that of the equal sign. So that is also an important feature of what we're doing here in the introduction. So we can move forward with that. That we have the equation ax equals to b has a solution if and only if b is a linear combination of the columns of A. So that means that when we put this together, and they have a great example here of this matrix with 3 columns, 3 rows, and B1, B2, B3. For this to be a consistent possibility, we must have a system that could be augmented and split up. And the system must be writable essentially in row echelon form, and we usually write it in reduced row echelon form. So what that is essentially saying is the following, that if you've got a system AX like this, A1, A2, A3, that ultimately what we want to be able to do is we want to be able to write this system, the augmented system, as 1, 0, 0, 1 with a solution. We'll call that C1 and C2. Okay, so we ultimately, for our purposes, we did Ghost Jordan, is we want reduced row echelon form for this to come through. Sometimes that's called RREF. Okay, that's an important little acronym there, RREF, reduced row echelon form, especially if we're going to do some of these on the calculator on our simple labs and stuff like that. That's kind of a call that we can use to do that. So this leads us to a nice little theorem here, theorem 4, which is an important theorem for us. We'll talk about that. Let A be an m by m matrix. Following statements are the same or logically equivalent. That is, for a particular A, they're all true or they're all false. So the first statement is that for every B in Rm, the equation has a solution. So to have a solution, what does that mean? To have a solution, it means you can write every B in Rm as a linear combinations of the columns of A. Also that the columns of A span Rm, and every point A has a pivot position in every row. What this is actually saying also is that this system is reducible. Okay, that we actually have, it'll be reducible, reduced row echelon. Now I lost that, I'm sorry, here we go. Okay, so it's saying that if you can do this, then your augmented matrix can be reduced to one solution, essentially. Okay, so it means that this ultimate solution, this has one solution, not many solutions and no solutions. So that unique solution that we had before is possible. Now we might go back and make sure we understand what that means and how that might look if it doesn't do that. And a way of seeing that is looking at some result examples here where that wouldn't work. And I'll give you an example here. If we actually augment a solution, we have 1, 0, 7, 0, 1, 3. This shows the solution is x is equal to 7, y is equal to 3, or if you want the b value, the solution of this system is, we might write that x, y is 7, 3. So that's the solution to the system, one unique solution. Now, a counterexample to that might be something like where we got maybe 1, 0, 7, and this ended up in a solution where we had a row of zeros. So in this case, this gives me a solution here of zeros, and this only gives me x is equal to 7. Y can be anything, really, because any y value will be able to do that. So that tells me, if you think of it graphically, if x is equal to 7 and y can be anything, that actually corresponds to a solution that is a line, right? In that case, it's actually talking about x equals 7 being the solution. So anything that's along the solution y, x is equal to 7, that whole line is going to be a solution. So x is equal to 7, so the point 7, 3 is a solution, and the point 7, 0 is also a solution. So that's an infinite number of solutions, and that tells you there's not a unique solution. So a lot of this stuff is not going to work. We're not going to have a single solution for that. It's not going to be a linear combination of columns of A. All of those things are going to come out. Another possibility is the absolutely no solution, and that's where two lines, remember, are parallel, where they don't meet. And that might look something like this, where you have 1, 1, 0, 0, 1, 7, for instance. That solution, that system, is going to be a little less obvious. It looks like there's a solution. Actually, that one actually works. Sorry. We're going to do 0. Sorry. Make it look different. Let's make it look different completely. Let's do 1, 0, 7, and then 0, 0, 1. That is going to be a problem. Let's see why it's a problem. Well, this is going to say this line is easy. It says x equals 7. We saw that wasn't a problem. But this one says that, well, if x is equal to 0 and y is equal to 0, this is equal to 1. This is telling me 0 is equal to 1, which is inconsistent. Okay, so this is a contradiction. So this is telling me that there's no solution. And this is a real problem. So that's why this kind of matrix, this augmented, is not going to work. And notice it doesn't follow our usual rule of reduced row echelon. We can get the 1 here up on the top left, but this one, when we reduce it or do row Gauss-Jordan, this whole row gets crushed, and we just have 0, 0, 1. So this is an example where we have no solution. Graphically, this is where these two lines are parallel, for instance, where there's no intersecting point. So we have to be careful about that. And that's what that means here. A has a pivot position in every row. That's obviously not true in that case. So the computation of AX, we can see an example here that if we start with a system 2, 3, 4, minus 1, 5, minus 3, 6, 2, 8, okay, notice how we compute that is we can actually multiply that through. So we have x1, x2, x3 multiplying through, and we get the system multiplied through here. Okay, so we can multiply the matrices out. So that's a great way of computing AX. It's another way of computing it out. So again, in this example here, if we wanted AX and we had this example, we would say minus 1 times the first row, second row, third row, and you could work that out that way. So it's just another way of multiplying the same thing out. Okay, and then there's some examples here for the computation of AX. The properties of matrix vector product AX are going to be quite obvious. So we have A times U plus V, AU plus AV. We can actually show some of these, and there's a nice proof here. You can see how if you do matrix A times U times matrix A times V, and you multiply it out, you can see that first of all you can do U plus V, and those are going to be actually in the matrix, and then you would do U plus V times the A1 like we did before, leading it, and then you can separate them later on and then separate them as U1 A1, U1 to A2, and then U3 A3 V1, V2, and V3. So you can see that that is the same as A times U and A times V, which shows you that A times U plus V inside the bracket is the same as AU plus AV. So I'll leave the other proof for you to play with, but you can see that it's going to be roughly the same thing. So we have some practice problems in 1.4 that you can work with, and then the solutions to the practice problem again in your interactive notes, and then you can move on to the next chapter.